So after introducing the concept of second-order differential equations that are homogeneous and have constant coefficients, I thought I would do a few examples that show the three cases in which the roots are either real and distinct, real and equal, or distinct and complex. So I'm going to start with the first example, which is going to be y double prime minus 2y prime plus y equals to 0. Now we know that we can actually find a characteristic equation. There's going to be a quadratic equation that corresponds to this one by simply replacing the order of the derivative by some power of r. So in this case we're going to have r squared minus 2r plus 1, because remember that this is the same as the zeroth derivative, and the zeroth derivative is just translated into 1, so there's basically no r in here. So now we're going to find the roots of this. We can either use the quadratic equation, or we can just factorize this straight away if we notice the relation. So that's just going to be r minus 1 times r minus 1, 0. So in this case we notice that the roots are the same and they're both real, so r1 and 2 is going to be equal to 1. So that's going to give us the solution. Y of x equals to c1 e to the power of x plus c2 x e to the power of x. Because remember that when we have equal and real roots, we need to add that x term so that both solutions are different. Now the next example that I'm going to show you is going to be for the case when the roots are distinct and real. So we're going to have the differential equation y double prime plus y prime, 5y prime, equals to 0. The characteristic equation of this is going to be r squared plus 5r equals to 0. Now once again we can factorize this, so that's going to be r plus 5 equals to 0. So what are the roots here? Well, r is going to be either equal to 0 or equal to minus 5. So we know that the general solution is going to have to form c1 e to the power of 0x. So this is just going to go to 1 plus c2 e to the power of minus 5x. And this is just going to be c1 plus c2 e to the power of minus 5x. Alright, so that's pretty straightforward. That's generally how you solve homogeneous second-order differential equations with constant coefficients. And now for the last example, I'm just going to include the case for which the roots are complex. So let's have the differential equation y double prime plus y equals to 0. So the characteristic equation is going to be r squared plus 1 equals to 0. Now how do we can use the quadratic equation, but a quicker way is to use factorization. So we know that when we have something like this, r squared minus 1, that can be factorized as r minus 1 r plus 1. Now we have a plus here, so what do we do? Or we might think, oh, maybe we can't factorize it. Well, you actually can if you replace that 1 by an imaginary number. So let's have r minus I times r plus I equals to 0. And does this give us that? Well, obviously the I times r terms are going to cancel out because this is negative, this is positive. And we know that I squared is equal to minus 1. So if we have minus I squared, that's going to become a plus 1, and it's going to leave us with that equation there. So yes, this is in fact how you would factorize an expression like that. So in this case, our roots are going to be plus or minus I. And if we remember from the last video, the form of the roots in this particular case, we're going to have the real part called alpha and the imaginary part called beta. In this case, we have no real part, so alpha is going to be 0 and beta is going to be 1, because that's what is attached to the imaginary number there. So the general solution is going to have to form equals e to the power of alpha x. Alpha is 0 in this case, so that's going to be 1. c1 cos beta x, so that's going to be 1x, plus c2 sine beta x, so that's just x, and this is going to reduce to c1 cos x plus c2 sine x. And that's essentially it. So you can see that there's not much of a science to this. Once you know what the roots are, you can pretty much just plug them into the general solution, and that's going to give you what you need to find. Now, things get a little bit more complicated when this term here on the other side is not 0, but rather a function of x. And in that case, we would be dealing with a non-homogeneous differential equation of second order. And to do that, we actually need to employ a few more steps to solve it. But this is the basic idea behind it, and we will be using this method in the following videos as well.